we're going to process, and we can show those markers going in. So we can also show where the middle is as well. So I'm going to calculate the middle. So I'm going to say the middle equals whatever left is and whatever right is. So I'm just going to do this operation. Why am I putting that in brackets? Yeah, because I need to do the addition before. If I didn't do that, it would do L plus R divided by 2, which is not what I meant. Okay, just like the reason we do it in maths. Right, so that actually will be 0 plus 4 div 2, which gives us 2. So our middle initially is there. So this could be search 1. So we need a number that we're looking for. So let's look for 25. Okay, so we're looking for search for 25. Okay, so we look at that middle position. So we compare the middle. So I'm going to compare 17 and 25. Are they the same? Right. Is 25 bigger or littler than 17? It's bigger. So which part of the list are we going to ignore? The left. We don't need to look at 5 and 12. They're smaller than 17, so it can't possibly be those. Right. So where do we position? So the right-hand side's fine, but where do we position this L? Yes, Toby.
Where the M was? Oh no, 1.
Yeah, 1 across from the M. So we need to put it there, don't we? So we can actually say L equals M plus 1, which will give us 2 plus 1, which equals 3. So we can put L there. So we've got on our start of our second pass through the data, we've got L and R in those positions. So this is search 2. Right, so we've got to calculate M again. So for this next one, we're going to say M equals, and it's the L and R. So we say L is 3. R is 4, and then we're going to do 2. So what is the answer this time? 3. Yeah? Everyone happy? Because we're truncating. So we end up with 3. So our middle is there. So we do our compare. So we say compare. What have we got? 21 and 25. Right. It isn't the number we want. Right. Is 25 bigger or littler than 21? Bigger. So if there was a left-hand part of the list, we'd ignore it. There actually, in this case, there isn't. So where do we put the L to mark? We put it at 4, 1 across from M. So again, we say in this case, L equals M plus 1. So L is currently 3, so that's going to make it 4. So when we do it this time, it ends up in the same place. But we don't know that. We're not looking at that. We're just going to do our calculation of M again. So when we calculate M for this final session, so we're going to go, so this is the third search. So M equals 4 plus 4 div 2, which gives us 4. So it equals 4. So this time we compare 25 and 25, and they're the same, and we found it. So one thing that you've got to get used to doing is how do we structure that nicely so that we can describe the process. They're not going to ask you for what is the code to do it, okay? But they are going to ask you demonstrate, and that's what we just did. Yes?
So essentially we're just halving the list every time.
Yeah. Yeah, so if you start off with 1 million items, you compare your middle and you say, right, do I need to look at the left or right hand side? Whichever I get rid of, my next search is just of 500,000 items. Then it's of 250,000 items. So actually in 2 searches, I've discarded 750,000 items that I'm saying, don't even need to look. You gave me 1 million items, 750,000 of them, get lost. Don't want them, don't need them. It's awesome as a search. There is really no better search. Not when you know something about the data. It always makes a difference to the algorithm. If you don't know, if you're data agnostic, you have to use more dumb methods, or what appear to be dumb methods. Okay? Exhaustive methods, as we call them. But when you do start knowing something about your data, you can start being a bit clever. A lot of human things that we do naturally are out of knowing something about what you're working with. When we look at the sorting algorithms, a lot of the sorting algorithms come out of the way that we do certain things. One of the sorting algorithms that we're going to look at is insertion sort. That comes out of how people play cards. When you've got a deck of cards and you've got a hand, and you're trying to make it easier to read, you'll often try and like fit cards so they're in like ascending order in a suit. And the insertion sort follows that method. So you like work backwards, so it fits there, or it fits there. And we'll do the same thing with insertion sort. Okay? Right. Yeah, I'm going to say, oh, go on, ask your question. Just go.
But for short lists, wouldn't linear search be a bit impractical?
Yes. Definitely. If you've got a list this short, I can't write 1 million numbers on the board, but if you've got a short list, you can see we had to do quite a bit of work there, didn't we? Yeah? Which is what I wanted to demonstrate. Tons of work involved. All these like adding up, dividing, comparing, moving the pointers left and right, doing another thing. All that took time. If we had a list that was only 5, it would have been way quicker to do a linear search. Because we just say, yeah, start a nut, add 1. Is it up? No, forget it. Okay? So that is an important, that is what we would say is a high level response question. So it's like going a bit deeper into why. Anything that is why and how. That's what we got nailed down for GCSE. Most of it is fact, isn't it? But there is that, when you start like thinking, well, what's the best one to use then? You'll see that when we look at the sorting algorithms as well.